Okay, in this part, I'm going to talk some important questions. So generally, there are four questions, and we will go through them one by one. And generally, they are about some interesting facts, whether or it's outside our methods. It's about how we analyze the results. So first one is about whether at least one of the predictors is useful. Yeah, because sometimes we collect a lot of data, and we have some predictors, and we have a response value. We want to assess whether these predictors will help us to predict the value y or response. And this is about like only at least one. It means that whether it helps or not. The second one is more detailed. It's about which part of the predictor is useful. And the third one is it's about the fitting, like how well does the model fit the data, and the last one is about the prediction, like how accurate. We give a prediction, but we don't know whether it's accurate or not. Can we estimate this from the training data? So this is like four important questions, and we will go through them one by one. And this is the first one: is there a relationship between the response and predictors? So statistically, we would do that in this way. We make an assumption, which is often called the null hypothesis. Our hypothesis is that all parameters should be the ground truth parameter coefficients should be zero. So zero means that there is no relationship between x and y. Okay. And alternative is that at least one beta is non-zero. It means at least one of the predictor is correlated with the response. So how can we calculate this assumption? This is tested by computing the F statistics. This term is kind of hard to interpret in this book compared to other objectives in this book. So here we have some concepts. So the first one is TSS. This means the total sum of squares, which means that you can understand it as a variance of the response. And another term is residual square sum of squares. This means the variance of the data after you have made some prediction. Okay, so I guess we can find some term here, like total sum of squares means we calculate the difference between the response and the mean, and we make a sum of all the difference. It's kind of like a variance of the y, and residual sum square means the difference between the prediction and the ground truth. So how can we interpret them in a like intuitive way? Like total square is like a variance of the y, and ISS means if we have made some predictions, then we have something left, which is one we cannot minimize, or we can like interpret it as epsilon, because we have make some predictions with x using x. So it sometimes in most of the cases it provides us some information, so we can compare it to the variance, which is just compare it with the mean value. We in most of cases we can give some information, so make our prediction is more close to y because it's case by case. We have some information over x, and we use x to make the prediction, which is y hat, and y hat can be a little bit close to the ground truth. So, but it is still imperfect. So we still have some values left to estimate, which is the residual. Why we call it residual, because it's remained by our estimating. So we can see that generally can be described in this way. This is the total variance, and this is the residual sum of squares. And if we have a look over the numerator, we can see that if we use TSS to minus residual sum of squares, we have the left part, which is because we have talked about that. This is the part we cannot explain, and this is the total variance. So the left part is what we have explained with the x. So this part describes how we get how much percent we get information, not percent, the value of information, the amount of information we have get from x, and by divided it with p, we get the average amount of information we get from x to estimate y. And but why we need so the only question here, left question here, is that why we need the denominator. Here, from my perspective, it's more like a normalizer or a value to help us compare. Because if we only have the numerator, we do not have a conceptual like percent understanding of like how much percent we have estimated value, because it's just a value. It can be 100, it can be a very small number, but because it depends on the meaning of this month. So we need a value to normalize it. That's why we have the denominator. The denominator here means the ISS. We have talked about it before. It's residual sum of squares. It means that let's say the left part we cannot estimate. So it's kind of related to the epsilon, which is the internal value statistical y we cannot estimate. So till now we can get a full understanding of the web statistic. It is a comparison between it's used the left part, the amount of information we have explained with x to compare with the left part we cannot explain. So so generally this does not tell us a lot, but if we have a look at that, whether in which case the value would be very large or very low, we can get a full understanding of this. So in which case this would be very low. It is case that the left part is equal to 0. It means that we do not have the x. When we try to use x, we get no information to help us to estimate the y. So I look at it here. If you do not get any information from x, your predictions can only be the mean of y. In this case, ISS would be close to TSS, because for H1, for any of the data, your prediction is the mean of y to make the minimal, right? Because you do not get information from the specific x of the data. I mean the x from the specific data. You can only give the mean of the y because you always have access to the statistical of all the y's. So you just give the mean of y for each prediction. So by replacing all predictions as the mean of y here, we can get the same equation of TSS and ISS. So generally they are the same. So in this case, we have no information from x to predict y. So the two values would be the same, generally the same. So what we can get is that we have very short, we have the long part of ISS, and we have very short part of the explained part, which is the nominator. uh, numerate, then the value would be close to 0. And in another case, we try to investigate in which case this would be very large. This is a case that when this part is very large compared to ISS, so it is case that ISS is very small. So in which case ISS would be very small. You can see that why it's when we get some information from a predictor, from the X, right? So if we get some information from X and they have a very clear relationship, and we can predict it very accurately. But remember that this whether we can okay. So let's first I want to mention that in this way. We try to consider a most simpler case. When this is close to 0, it means that we predict it very accurately from with the help of X. And then this part would be very small. This part would be very large, and so this part would be a larger number. So large number or F means that we get a large amount of information from these predictors. Okay. So in summary, so for the first case, so the F indicates like how many information we get from the predictors to explain or to predict Y. And also, I want to add a hint here about the value of ISS, what I'm trying to talk about before. So the ISS also have depending on the TSS, because when we try to estimate this, the value could be very small, because as I mentioned before, if this response is a small value, like its predictor tiny cells, some properties over tiny cells, so it can be very small. But if we are predicting some big markets, the value can be very large. So the residual square sum of squares does not handle it, because it does not have a normalizer to help it to scale to a good value scale. So that's what we have to do with TSS. Because TSS here, it describes variance. So if the data set is for a small value with a response over a small value, then it will be a small number, and then it can be used to normalize the value. So we can always use trust F statistics because it can be normalized for different data sets. Great. That is how we get value. So generally, it's not a perfect plan, because a lot of value is estimated. Here we want to use epsilon, but in both cases we can only estimate it. So in general, we can only estimate it with from a general picture. When it's close to 1 or 0, it means that there is almost no relationship between X or Y, or we cannot estimate Y from X. And in some cases, very large, like in this case, it's almost 500. So it means that we have a very small ISS compared to the explained part. So it means that these predictors helps a lot for us to predict Y. Okay, great. And this is how we can use F statistics to judge the hypothesis, null hypothesis. Like each one is not useful, and so if its value is very large, we can reject the null hypothesis. Then we can say that at least one predictor is useful for us to estimate y. And also, next part is about like the author use it to estimate some part of some incremental helps of some predictors. Generally, the form is similar, but it replaces TSS to ISS 0. So it used to compare like we have two models which use one of them use maybe part of the parameters and another model use add some new predictors, and we want to say that whether the new predictors help to estimate y. So this is a more general case because the previous one, what we mentioned, is a special case where the predictor set is null. That means there is no predictors compared to some predictors. And this is a comparison when we use some predictors with some actual predictors. Okay. So that's generally how we use F statistics. And the following some points I also want to mention or want to address. Like the first question is about like whether we can use the individual estimation of the effect of each value to replace this question, because in this part we try to talk about at least one of them is useful. And we did have some like p-values before to estimate whether each variable for each individual is useful for a final prediction. So if we found in some cases we found that all of them or each of them, some of them is lower than 0.05, which means they are very distinct. Obvious connection between this value and the final results the prediction between sum over x and y. So can we see that in this way? We can we say that we at least have one, because we already checked each of them and we found that some of them have a distinct connection between y. So in this case, can we see that at least one of them is connected to y? And nature question would raise that why do we need to use this F statistics to estimate at least one? Because we have already checked each of them, why we need this to estimate at least one x is connected to y. And this is so in this part it also says that they are totally different things. So to explain this, we need to recall that the concept of the distinguished value, which is 5%, 5%, in that the probability that this value is connected to is not connected to the y is lower than 5%. So it means that when we have a very large p, like p is 100, in most of our case, we would have around 5% of the coefficients have a lower value than 0.5. That's the meaning of the p-value. So this case, so this explains the question, like if we investigate each of the values, and we can always see that some of the values is below our minimum bar, like 0.05, but in this case we cannot say that they are distinguished obvious connection between sum over x and y, because it could be like causal reason or probability. So in this case, we need to, that's also why we need to estimate the F statistics for all the values, like at least one. So this part explains that why these two concepts is different. Okay, great. So this is the first small question, and the second one is about the problem of F statistics. So what I also mentioned here is that F statistics rely on an important fact to work. It requires that we can fit a model because we use the residual of our prediction to estimate the F statistics. So the condition is that at least we need a model. But in some cases, we have very large P compared to N, which is the number of the samples. So in this case, we cannot even make a prediction by creating a model. So this case causes some problems, right? Because we cannot even get a model, and in this case, we cannot get a residual sum of squares. So in this case, we cannot estimate F statistics. Okay, great. Then we move to the second question. The second question is about how the deciding on important variables. So this is the continuum of the first question. In the first part, we talk about how to decide if some values are connected to the y. So we may get a conclusion that some of values is connected to the y. Some of x is connected to y. And the next question is that which part is connected to y? So we need to decide on important variables. Okay, so this one is generally easier to understand. It just includes three methods: forward selection, backward selection, and mixed selection. They're generally about how to select the predictors that we are going to use in our model. So let's get started from a naive solution, which means that we try to select use each method. Like we have like maybe earn p coefficients or px, and we just check each of them. Then by using this, we can see total combinations of 2 powered by p. So if we but this is not a good solution because if p is moderately large number, which is 30, we can get all solutions of this number of models. This is a very big number. We cannot estimate all of them. So we need some simpler solution. We cannot just search for each combination. So there are generally three kinds of solutions. And the first one is, so in summary, they are all about a greedy method, but they have like different techniques. First one is very easy to understand. It's forward selection. So we start from a null model, which means that none of the predictors is included. So in each step, we include like one more predictor, and now we can get we try to fit the data, and we can calculate ISS. And for this step, we select the lowest one, like we select 4 predictors one by one, and we found the second one have the lowest ISS. Then we include the second predictor. And by continuing it, we can stop in some like step, because when we move on, maybe in the we totally have like 8 predictors and go to the 5 step. When we have already selected 5, we found that including the 6th one would not decrease the ISS a lot. Then maybe we can stop in the 5 steps. Okay, that's how the forward selection works. And second one is backward selection. It's just work in another way, like we have 8 predictors, and we just start from model that include all the predictors, and we can in first step we try to remove one of them, and we may find that remove the fourth one is the best choice because it has the lowest ISS. Then we move when we are trying to remove something, we always increase the ISS, but we can find one of them is the minimum. Okay, so it does not increase the ISS a lot. So then we choose this one. Then we do it again and again until we reach some points, like removing any of them would get results in a large increase of the residual sum of squares. Okay, great. This is the second one, backward selection, and last one is mixed selection. It looks like a pro version of RSS, pro version of forward selection. So during the forward selection phase, the motivation is like this. When we are doing forward selection, maybe we just have to do it to the fifth step, and we increase one value, and we found that it can replace some of the previous values. Like we have put a very important value in the fourth step, fifth step, and we found that in this case, if we remove one of the previous predictors, like the second one, we do not increase the residual sum of square errors. Does not increase a lot. So in this case, we can remove the second one after we have introduced the fifth one. So since can happen in many cases, so generally it's about when we are trying to introducing some new predictors into our model. At the same time, we can check if some of the previous introduced is not useful. So the theoretical motivation behind this is that some of the variables is correlated. Like we have 3 variables A, B, and C, and maybe in first step it's great to introduce C because it includes some part of the information or A and B. So generally the information or C is the largest. So in the first step, we should introduce C. But after some step, we have introduced A and B. C becomes less informative because all its information is from A and B. But if we already have A and B, C is not that useful. And A and B, the combination of A and B provides some unique information belonging to AB itself. So in this case, C becomes less useful. So the mixed selection strategy overcomes some drawbacks or problems of forward selection. So it can be seen as a combination of backward selection and forward selection. So generally, these 3 methods, from at least from the method part, is easy to understand. So in summary, they are just like using the residual sum of squares as an indicator of whether some predictor is useful or not. Then use it to make selections. And the overall structure is to minimize the computational cost by using some grading search algorithm. So in the first part, we introduce how to have to know that at least one of the x is correlated to y. And in the second part, we investigate how to select important y rows. So now we can have a model, and in the next part we will talk about model fit, like in how much percent the model can fit data. So at first we need to recall a concept called R-square. So after we have introduced statistical, the concept of R-square becomes easier to understand. So denominator is TSS. It means the internal variance of the data of the y, and we can, after estimation, we can get residual sum of squares, which is the value of a part that we cannot estimate with x. So if we use the first term to minus the second one, we get the part we have explained. So generally we compare to the part we the total variance of the data, we can get a value. And if it's very large, it means that it means we will have explained a lot, right? And if it's close to, because we have a sum, so this value must be between 0 and 1. So if the model is reasonable, because the lower bound of the model we can get is a model which always gives the average of y as the prediction result. So it cannot be larger than TSS. So generally the value of R-square is always between 0 and 1. And when it's 0, it means that we do not explain anything better than the random guess. And when it's close to 1, it means we have make a good estimation. Great. So generally, after we have known some concepts of R-square, this we can understand this point, this part, general idea of this part. So we also just mention some small points, some points need additional attention. Okay. Great. So we also give an example of like advertising the relationship between some points and sales, between some variables and sales. And when we try different combination of the predictors, we can get different R-square. And some by introducing some of them, we can get a lower R-square, which means that they are sometimes meaningful. But there's some points we need attention. And first one is that R-square will always increase when more variables are added to this model. So even when you are trying to add some noise into the model, we will get a lower, higher R-square. But why? Does it mean that this variable is useful? Actually, no. So R-square is connected to overfitting because it's calculated based on how much percent we have the noise prediction based on the training data. So even though when we are trying to inject some information of the noise, it can offer some information over the prediction results because we can try to remember noise, like some noise is connected to the prediction results, and we can try to connect it up. So in this case, it can help to decrease the training error. So that's why we call it overfitting. When we're trying to introduce some predictors in the noise, we can have a lower value of the prediction. Okay. So after this, the author also mentioned some value of Roscoe square error. So recall that radical square arrow has a strong connection of the residual sum of square, and generally they are normalized and um, a root term of the ISS because sorry, not because um, so important thing need to mention is that when we try to introduce more predictors, the value of the ISE can even increase. So it's kind of different from the I square because I squares they are always decrease. So but why? It was mentioned that the ISS will always decrease because after introducing some values, the prediction on the um, training data will always be more accurate. So we have lower ISS. But it does not mean that ISE will always decrease because we have another term here. When introducing more predictors, we have a lower denominator here. So we will have an increase of the value in some cases. So models with more variables can have higher ISE if the decrease in ISS is small relatively to the increase of the P in the denominator. And this is the second part. Second thing we need extra attention. And in the last part, I also give a illustration. Actually, I don't know why it's put here, but I try to convey the main idea of this. This is a 3D plot, and the z-axis is for y, and we have TV and radio as the predictors. We can find that there's some like pattern for this figure about the arrows. Like so the model in most cases would over pessimic one over spending is spending to exclusively TV or video, but it's too pessimistic when there's a combination of them because we can see the actual value is higher than what our prediction. So yeah, we can infer it in this way. Just a problem is that I cannot find a connection between this interpretation and what the model also trying to convey here. So I would just treat it as an estimation of the model by illustration way. Okay, this is about how to estimate the fitting of the model from some statistical values. And the last part is about predictions. So it has strong connections with the third part. So generally, we have three sort of uncertainty associated with the prediction. So it can also be said that we have three kinds of errors. So the first one is coefficient because what we are get the coefficients we get here is from the estimation. So it may have some difference with the two models. And the second one is the model bias, which means the bias we caused by the selection of models. Like the real world can be linear, but we select a linear model. So this this is the second part, which we call it model bias. And the third part is irreducible error, which means that because it is always some noise in the data, and also we can introduce some miss to introduce some important predictors, some extra predictors which is not in our data. So there can be some values in from some information in that in these predictors. So for this part, we can not reduce them because we do not have any information, even though we choose the best model and we estimate the coefficients perfectly. So generally there are three parts. The first part is efficient, and we can avoid it by optimize the training process. And the second part is about model by can reduce them by select most appropriate model for this problem for this data set. And third one is in reducible. And after the three concepts, we can understand the uncertainty of the prediction more systematically. And finally, we want to introduce two terminologies. First one is confidence interval, and the second one is prediction interval. So at first, I want to. They are both about probability intervals. It's like we have a Gaussian and we have a range of the predictions that we say we are confident, like maybe some percent that this is correct, and we have a range, right? So generally, they are about like talking about uncertainty or confidence, like how much of the range, because we already have a prediction, right? And the question may raise like, oh, you make a prediction, but I don't know like what's the range of the two values, like over the ground truth. So I need you to give me a general response, like instead of just the value, you need to tell me that how accurate is your prediction. And this is estimate. There are a lot of ways to describe this. We cannot say that 100% or 1900% that my prediction is correct. This is the right way, because from the mathematical view, the probability of our prediction is correct is near to zero. So a more appropriate way to describe our prediction is that I have like 95% confidence that the true prediction is located in a range or interval between blah blah and blah blah. Okay, that's why we need the interval here. So we have two different intervals, and the first one is great. But why the problem is why there we have two kind of intervals here. So we need to distinguish. The first one is confidence interval, which responds to questions and the prediction of fx, because we have fx and fx plus epsilon, which is a noise. So prediction error is about after we have introduced the noise, which is the ground truth. But confidence interval answer the question that whether our prediction is close to the ground truth or f, not include epsilon. We just want to like answer the question whether prediction or the value of fx is in which range. Okay, great. But besides all this, we also have some uncertainty of the epsilon, which is internal uncertainty over the data. And we, in this case, we had a broader range. So to answer this question, we need to plus another Gaussian. So we can see that the second prediction interval is larger than confidence interval. So in summary, confidence interval answer question that what's the range of the true prediction fx comparing given your prediction at some point. The point must be the middle of these two numbers. And the second question, the second prediction interval answer question that what's the range of the two cases, like the specific case for the y for this data point, like in 95% confidence. So it needs a broader range. Okay, great. So in this part, we talk about the predictions, and we try to decompose it into 3 parts, and we try to give intervals on all our predictions instead of just a single data point. So this big section answers 4 important questions. And personally, I also believe this is an important part, help us to understand something beyond the models. If you have learned something about machine learning, then this part is best talked in that kind of book, and it's only in this statistical learning book. Great.